So in this video, what I'm going to do is I'm going to take you through this second exponential analysis worksheet where we needed to create a graph of a function. We'll go through how we analyze it, and then we'll also talk about the transformations from the parent function. So our first function is -4 times 1/2 to the x plus 8. Now, as we make the graph, we need to remember my big thing, my number one big thing. If you take almost nothing else out of this year, seriously, don't forget, because if you have me next year, if you're lucky enough to have me 2 years in a row, I know you're saying, you are going to hear me say the same thing. Make a table. You need to make it yourself. I didn't make one for you now this time, okay? So you got to find room. You could put it on separate paper. Other things that I want to see, okay? And this is just based on what I'm seeing from some student work, okay? I want to see arrows on both ends, okay? I'm seeing some people getting a little bit lazy. And look, if you want to get lazy with the asymptote, I could potentially live on that with that, depending on how lazy you get, and you'll see me in this video maybe show you an example. But you need to put arrows because it does still go on forever in both directions. Positive infinity on the x and negative infinity. So that is pretty important. The other thing is make sure I want to see clear points. Okay. I want to be able to clearly see what your x and y coordinates are. I shouldn't have to do a lot of guessing, so maybe try to make those nice and dark if you can. I would appreciate that. Okay. And then, of course, making the table. And if I think of other things, I'll add it to this list. So those are things to think about. So let's get started. Now here we need to make a table. I don't have a lot of room here. So what I'm going to do is I'm going to make some scrap paper. And I'll make a table. And then you know what I'll do? I'll just copy and paste that back over. Mr. Moray and his tech skills. So now that I've had the opportunity to do this, you might be able to see this better than it was on your paper. However, it seems like people are able to get it okay. Now remember, B is going to be, not obviously, I apologize, it is going to be a half. Remember, the number in here, if you're ever wondering, remember that it's defined so that it must be greater than 0. It can never be a negative number, because remember when we talked about it was geometric sequences, we talked about how they would alternate if that was a negative number, and we can't have that happen with a exponential function. Okay, so just be aware of that. Now we're going to start to plug in some numbers here, right? That's why I always say make a table and start to plug in some numbers. And, you know, right, at some point it's going to go off the graph and we're done. And then on the other point, it's going to start to get really close to a number, and we'll hopefully be able to figure out what that is. Okay, remember our usual observations here that we make. -4, a is less than 0. So that means we should be below the asymptote. And remember, this is special. This 8 is special when it comes to the asymptote. I know it was originally a 7, but I had to make it an 8 to make it just a little bit nicer. Hopefully you saw that it was an 8. So let's start to plug some stuff in. Oh, and also, I'm sorry, one last thing. B is between 0 and 1. So what that means is we're going to go closer to asymptote as x gets larger and larger, right? So when you have, remember, when you have a b value that's more than 1, you're getting further from the asymptote. When you have a b value between 0 and 1, greater than 1, further. Between 0 and 1, you're getting closer to the asymptote. Okay? So that's one thing to know as well. So let's see what we got. So I'm going to plug in 0. I like to plug in 0 because anything to the power of 0 is 1. So that means a half to the 0 is 1. Negative 4 times 1 is negative 4. And negative 4 plus 8, not 8, negative 4 plus 8 is 4. All right, now I'm going to plug in 1. So 1 half to the power of 1. Remember, anything to the power of 1, you get the same thing back. So 1 half to the 1 is a half. Negative 4 times 1 half is negative 2. Negative 2 plus 8 is 6. All right, and look, eventually we're going to go off the graph, or maybe not, we'll see, right? It's just, you just have to have the patience. Give it a chance. I promise you, just give it a chance. All right, 1 half to the 2. So a half to the 2, I'll do this a little bit more visually, is a half times a half, and that's equal to a quarter. A quarter of negative 4 is negative 1, and negative 1 plus 8 is positive 7. Huh. Interesting. Starting to go up a little bit slower, right? We went up by 2, then by 1. What about this? So a half cubed is a half times a half times a half, and that is equal to 1/8. Negative 4 times an eighth is equal to, right, negative 4/8, which is a half. And because it needs to be negative a half, right, because you have a positive times a negative. So negative a half plus 8, 7.5. So you can see that it's starting to trend towards a number. I wonder if it's this one. All right, I'll do one more. 4. A half to the 4th, that's 1/16. So you get negative 4 over 16 because it's negative 4 times 1 over 16. And that's a quarter. Negative 1 over 4. And a quarter plus 8 is 7 3/4. So you can see we're going towards 8. So now I'm going to start going negative. Negative 1. Remember, a half to the negative 1. Remember how this works. First, you flip. Then you make the exponent positive. Now 2 over 1, that's the same thing as 2. So it's 2 to the 1, which is 2. Then we have 2 times negative 4, which is negative 8. Negative 8 plus 8 is 0. Now, if I do 1 half to the power of negative 2, right, let's say I plug in negative 2 for x, well, what's going to change? Well, the flipping is still going to happen because it's a negative exponent. 2 over 1 will always be equal to 2. That's not going to change. So now we're going to do 2 to the power of 2, and that's 4. 4 times negative 4 is negative 16. Negative 16 plus 8 is negative 8. So we have a nice table right here. So folks, I know it's tough to make a table. You don't want to always make a table. It's a lot of work. But this is what I'm telling you. 1, if you can focus on the patterns that we're developing here, and 2, you can replicate those patterns in these new problems, you can make the process of plugging in easier, so that making a table is actually not that bad of a strategy. All right, if you believe in what I've been teaching you, then you know that this has come up over and over again. It's one of the biggest themes of this year, is we've talked about different functions. So then you know that making a table has been the only strategy that's ever helped us figure out any single one of those functions. There's no other way. We've talked about with the all kinds of rules, right? The 1, 3, 5, that doesn't always work, right? Just look at the slope, that doesn't always work, right? With the rise over run, making a table always works. Now, in the past, and in the future. So I know sometimes it might seem annoying, that I keep talking about it, but there's a reason that I do that. So I'm going to come ahead and I'm going to paste it. So go ahead and paste this table in here. And just going to move some stuff down here. Actually, I think I might have to move stuff over a little bit more. So I'm going to move this down. I'm going to block some text out, and then I'm going to delete the table. But if you rewind this video, then you can see what points I had. All right, let's plot. So 0, 4, right? Because now those right, X and Y's in the table, right? I like to write, I like to write Y. They're the same thing, Y and F of X. So 1, 6. So these, what I'm getting at is these are points in the coordinate plane. These points in the table. They give us this picture of what the function looks like. Okay, so what do we see? Well, interestingly, we see this very nice asymptote at 8, right? It starts off at negative infinity, right? Going in that direction. And then as x gets bigger, and in the window we see, as we get bigger, we get closer and closer. And we come alongside, and we don't really ever touch it, but it looks like we're going to. This value of 8. Okay? So this is more or less what your graph should look like. I just want to make sure this is 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 would be up here. Because this graph actually, for whatever reason, goes to 11. All right. So making a table is just so helpful. And look, here's the idea. Notice I got a little bit lazy here. I said, look, I can see it's going to 8. It's getting close to 8. I'm done plugging in points. I got lazy. But notice some things that I've been asking you to do. First, arrows on both ends. You can see I put an arrow here. I put an arrow here. Please do that. It's so important. And then as you could see, I made clear points. So every single point on my graph was backed up. You could see, oh, now I just made them clearer, but before I made that clear, you could see there was a point there. So really help me. First of all, it helps you make sure you know your points are right. Second, it helps me know what you were thinking at the time, so that what that allows me to do is offer you feedback. Either you're doing great, perfect, keep up what you're doing, or here's some things that I want to think about. When you don't make a table, I don't know what's going on in your head. That's important. Okay. Now I'm going to talk about analysis here. So let's talk domain and range. The domain, as with any exponential function, is negative infinity to infinity, while the range is negative infinity, and I know that because of the arrow, to 8 with a closed bracket or parenthesis, because remember, it doesn't get to 8, it gets close, right? So we saw it going 7, 7.5, 7 3/4, probably 7 7/8, 7 15/16, right? But it never gets to 8. Like if you've ever counted like 9, 9.5, 9 3/4, 9, and if you ever had someone do that when they were counting, it's the same idea. Getting closer and closer to the number, but never actually getting to the number. Okay? Where is it increasing? This function is increasing everywhere. Now remember, one thing about an exponential function, and this is something that might be confusing us on the work, it always is either increasing or decreasing. So for every single one of these analysis, I should see one of these will be this empty set, nothing, null, NA. This other one will be negative infinity to infinity. So it will either be this setup here, or it will be the other way around. Those are the only two possibilities for an exponential function. Okay, and even though it's increasing by very little, right, it's still larger as you go from left to right. All right, positive. Where are we positive? So here, and no surprise, I tried intentionally to create a graph, and that's why that 7 became an 8, where we would have a nice x-intercept. So it's positive. So when we get to -1, that's when it's 0, right? That's the border between positive and negative. And then so it's -1 to infinity. Where is it negative? From negative infinity to -1. And then the x-intercepts are -1, 0. And that's it. And the y-intercepts is 0, 4. And remember, the y-intercept, you're always plugging in 0. We don't have any strategies for finding the x-intercepts here because we don't know what are called logarithms, which are the opposite of exponentials, right? They're like the multiplication to exponentials division, right? In that sense, right? Those ideas of undoing. All right. Horizontal asymptote, here it's going to y equals 8. This does need to be an equation. That's very important. The y equals makes it a flat line. If you do x equals, it will be up and down. The 8 makes the flat line go along the graph, and it makes it have an intercept. So, right, because this is like 0x plus 8. So no slope and an intercept at 8. So it's always 8. Okay? End behavior. As x goes to negative infinity, f of x goes to negative infinity, and as x goes to infinity, f of x goes to 8. Okay? One more thing. What specific transformations occurred to get from the parent function to this? Remember, I always recommend you graph the parent function. This is the parent function. 1/2 to the power of x. So it's like 2 to the power of x, but it's been reflected about the y-axis. And that has to do with the fact that the negative powers are tied to the reciprocals. And so that's exactly what we're working with, is with reciprocals. So rather than get larger as x gets larger, it gets smaller, right? Because when you multiply a fraction by itself, that fraction is just going to get, I guess not smaller, but closer to 0. So what's the transformations that occurred here? First, we have a reflection about the line y is equal to 0. Now, there is more than one answer. We can talk about that in just a minute. Reflection over y equals 0. Second, dilation by a scale factor of 4. And then you have translation up by 8. Now, algebraically, if we reflect this, so if we start with y equals 1/2 to the x, so if we start with y, and the y and the f of x, it doesn't make a difference in terms of this analysis. If we reflect over y equals 0, that essentially means we have this graph right here, reflection over the x. So you're taking all the y's and you're flipping their sign, and that reflects over that x-axis. If we then dilate by a scale factor of 4, how I would interpret that is you're taking this, and we'll talk more about dilations next year in course 2, is now you're multiplying those outputs by 4. So you're dilating, you're stretching. And then if you say translation up by a scale factor of 8, you're finally saying take all of the y values and add 8 to them. And if you notice, that's exactly what we've got. Now the order doesn't matter. If I had flipped these around, the translation and the dilation, if I had done the translation first, what I'd have is negative 1/2. Actually, let me do this in a different color. If I had done the translation first, what I would have had is, so I would have done the reflection, then I do the translation. Now, if I was to dilate by a scale factor of 4, well, yes, I would have to multiply this output by 4. But I'd also have to multiply this, because if you want to multiply the whole output, well, what you're actually doing here is you're taking 4 and you're multiplying it by, well, what's the output? How do you define that? Well, the output is negative 1/2 to the x plus 8. So you can see you actually get a very different function. So you have to think about the algebraic impact of the various transformations that you're making. All right, folks, and so then here we are at problem 3. I think I might have, oh no, I didn't mess up my number because problem 2 was the transformations. So problem 3, we're doing a very similar thing. In preparation this time, I did go ahead and make another blank sheet so we can talk about this. So we need to make a graph of this function. It's 3 to the power of x plus 2 minus 9. Keep in mind, we are going to have to think about the parent function as well. So similar observations here. First, I noticed that the b value is greater than 1. Okay, the b is more than 1. So it's going to be getting further from 0. As x gets greater and greater, getting further from 0. Okay, and then or because what I should say is, when I say further from 0, if you think about it, it's the value of this that is getting further from 0 or closer to 0, not this. And then so when it's close to 0, then negative 9, right, is the only thing that's left, and that's why the negative 9 is very closely related, as we can see, to the asymptote. All right, let's talk about a table. So we have, I'm just going to erase this box real quick. And one thing I didn't do was I didn't go ahead and grab this one in advance, but I now have it. And let's make a table. All right, remember, you always make the table. Give it a chance. And then that's an x plus 2. Yes, it is. Okay, so let's get started. Now, what are some numbers we could plug in? Well, we could plug in 0. Interesting choice, right? Why not? So when I plug in 0, I get 3. And now 0 plus 2 is 2. So it's 3 squared minus 9. And 3 squared is 3 times 3. And 9 minus 9 is 0. So when you plug in 0, you get 0. Huh. Interesting. Okay. All right. So let's try, I don't know, 1. 1 plus 2 is 3. So what we want is 3 squared minus 9. Uh-oh. 3 times 3 times 3 is 27. 27 minus 9 is 18. So bad news, we are not going to really be going any further. And in fact, I don't even want to graph this. I'm going to go with negative 1. So I do negative 1 plus 2 is 1. 3 to the power of 1 is 3. And 3 minus 9 is negative 6. I plug in negative 2, and lo and behold, I get 0. as my exponent. And so 3 to the 0 is 1. All right, and notice now that here, as I went up from 1 to 2 to 3, there was explosive growth, right? I went up by 6, and then all of a sudden by 18. Now something else is happening, right? Now I'm going the other way. Now all of a sudden I'm going only up by 1. Only, or I guess in this case, down by 1, right? -6, -7. All right, -3, what happens? So -3 plus 2, it's 3 to the -1, minus 9. And remember, 3 to the -1 is 1 over 3 to the 1, which is 1 over 3. So it's a third minus 9, and that's -8 and 2/3. Interesting. So, is there a pattern? And actually, I see a mistake. Sorry, folks. 1 minus 9 is not -7. Silly me. It's -8. Alright, that makes more sense. I was wondering what was going on there. Alright, last one I'm going to do is -4. So plug in -4. -4 plus 2 is -2. So I get 3 to the -2 minus 9. This is 3 to the -2 is 1 over 3 squared. And 3 squared is 9. So it's 1 over 9. Minus 9, which would be -8 and 8/9. Wow. So this is very, 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 very close to -9, right? And next we're going to get 80/81, 241 2/43, 728 729s, like almost. But again, mathematically, no. If the numerator and the denominator are not equal to one another, then you cannot do it. You can't say that that is 1 unless that numerator and that denominator are equal. There's just no way to do it. I apologize for whatever technical issues seems to be going on here. It's supposed to let me, there we go. It's supposed to let me be able to drag these, supposedly. So they say. Okay. So I'm going to move this down here for a sec. And let's see what we can do here. Now as we get more negative, it gets, so I can probably put my table right here and be fine. Alright, so let's see what points I've got. Let's see what I got. And I can move the table if I need to. We know where that is. And you can rewind if you need to see that. So I've got 0, 0. And 118 was already way off the graph. So we'll have to figure that out. 1, -1, I should say. 1, 2. 8, 8 and 2/3, 8. So here you can see we're getting real close to 9, right up next to 9. Okay, don't get lazy though with it, please, folks. And now we got to depict it really taking off. So come through 0. Like I kind of missed it a little bit, so I should go back and get that kind of, you know. And I mean, I take the time, you know. Show I know you care. I know you're good kids. I know you care. Show me you care. Make your graph show me that you care. You go through those points. You graph it through. You have it going up, and you put the arrow. And it doesn't have to be beautiful, but it should just reflect a strong effort, okay? Make it show the effort I know that you can give me. Alright, it's challenging stuff, but I wouldn't give you challenging stuff if I didn't know you could do it. Alright. Now, domain. Again, the domain. -infinity to infinity. The range. Lowest. It does not go any lower than -9, but it doesn't get to 9 because of the asymptote. It goes up to infinity. This graph is increasing everywhere, As you go from left to right, even if you're going up by a little, you're still going up. It's never decreasing. Okay, it's positive from 0 to infinity, because 0, 0 is that cutoff point, and it's negative from negative infinity to 0, right? Before 0, it's negative. After 0, it's positive, right? Before 0, it's negative. After 0, it's positive. Okay, x-intercepts. The x-intercept in this case and the y-intercept are the same because they're both 0, 0. The horizontal asymptote, remember that invisible that invisible line. Let's see. Let's do a little, I don't know, let's make it green. So this invisible line here, so to speak, I'll make it a little bit more narrow. That's that horizontal asymptote. It's representing that output that the function gets really close to, but it never quite gets to, and that is negative 9. Okay, end behavior. As x goes to negative infinity, f of x goes to negative 9, or in limit notation, the limit as x approaches negative infinity, and I believe this is actually g of x is negative 9. And then you write as x approaches infinity, f of x approaches infinity. Remember, you only do one or the other. The limit, and sorry, I get so used to writing f, it's g. The limit as x approaches infinity of g of x is infinity. So remember, you do either one, but just there's some individuals who will really love it to see that next year. You can do either one. They're both, as long as you do it mathematically correct, it's a full credit as far as I'm concerned. All right, now let's talk about transformations. So I have to do transformations from the function 3 to the x. Okay, so if we take a look at the function 3 to the x, here's what it looks like. All right, so we have 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, 3 to the negative 1 is a third, 3 to the negative 2 is a ninth, 3 to the negative 3 is 1/27th, and so on and so on, and we get closer and closer and closer to 0. Okay, so if you think about the transformations here, whoa, what's going on? So if we think about it here, if we go from piece to piece, and I think about the original function versus the new function. If you think about negative 2 in this function, when I plug in negative 2 to the purple, what do I get? 0. When I plug in 0, so think about it like this. We got 3 to the x. We've got 3 to the x plus 2 minus 9. When I plug in negative 2, what do I get? I get here, rather. When I plug in negative 2 here, what do I get? I get 0. Negative 2 plus 2. When I plug in 0 here, what do I get? I get 0. So plugging in negative 2 has the same impact on the power of 3 here that plugging 0 in does here. And so that, in a sense, explains the negative 2 versus the 0, that first, what we need to do, and this, there's two answers to this. You need to do, I would prefer you to say, translation left by 2 followed by translation down by 9. And if you take a point and you take its corresponding point guess I'll make this red. And you take this point and move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. Or 1, 2, 1, 2, 3, 4, 5, 6, 7. Right? You get to the partner point, the image on the transformed function. Last question. Write the equation of an exponential function that passes through force 36 and 2, 4. Okay, so remember what I taught you kind of over the past couple of days is that f of n, right? Remember, you're looking for this. F of x is equal to a times b to the x. Now, in a geometric sequence, what you know, and I'm just going to adapt this using b instead of r, is that if I take f of n and I multiply by b, it gives me f of n plus 1. So that means, right, if I take f of, I don't want to say 3, I actually want to say is 2. If I take f of 2 and I multiply by b, I get f of 3. If I take f of 3 and I multiply by b, I get f of 4. And so on and so on. But wait a minute, f of b, f of 3, that was f of 2 plus b. So if I combine this, f of 2 times b, I think I said plus, I meant to say times. So f of 2 times b is f of 4. And what's b times b? That's b squared. So multiplying once goes up by 1. Multiplying twice, therefore squaring, goes up by 2. Or in other words, right, we have this equation. So now, for these specific ones, or I guess for any, but we need 2 and 4, right? So I know that 4 times b squared equals 36. Wow. Okay, so I divide, b squared equals 9. So b could be, in theory, 3 or negative 3, but remember, in an exponential function, b has to be positive, so negative 3 cannot be an option. So b must be 3. So I have f of x equals a times 3 to the x. Now look, just like with geometric sequences, I'm going to ask you to choose a point and plug it in. So I'm going to choose the smaller number to make it easier. So if x is equal to 2, y needs to be equal to 4, according to this point right here. So 3 to the power of 2 is 9. Now I divide by 9, I get 4 over 9 is equal to a. Let's see if this works. So if I do 4/9 times 9, I do get 4. And let's see what happens if I do 4/9 times 3 to the power of 4. Let's see if I get 36. So 3 to the 4 is 81. So 4/9 times 81 is 4 times 9, which is 36. So my final function, f of x equals 4/9. And you don't have to have that dot. You could just do the parentheses. That's fine. Times 3 to the power of x. Folks, I hope you found this video to be helpful. If you stuck through the whole thing, thank you very much. I know this was a long video, but I did want to make sure I broke down exponential functions a little bit more, just so that anyone who needed some extra explanation could have access to that. Again, hope you found this to be helpful. Thank you so much for watching. Please feel free to like and subscribe so you can stay up to date on the newest stuff that I'm putting out there. Until next time, have a wonderful day. Don't forget to love math. And remember, you can do it.